my I wouldn't be if anyone has a question online, I think they'll have to maybe put in the chat or something. Or speak out, and then if it's in your computer, we can hear. Okay. So we wait a bit or start? I don't know if we are.
We're in Stanford
Well,
time, so we can wait a little bit.
okay, at Stanford time is 5 minutes.
Okay. California time, I don't know. Coming from the East Coast, I feel like everything's a little slower here.
Well, maybe we can start just with a bit of introductions in a way, because I given this course a couple of times already, but one was a week-long course, the other one was a 4-day morning and afternoon course. So condensing that into 2 hours is it's a bit of a stretch. So I tried my best. I put a lot of slides together, and then I thought, depending on what people like, I'll just skip some, or spend a bit more time on some. So maybe you could tell me, maybe hands up, anyone who has here been able to, or has, as part of the research, coded their own finite element code from scratch. Anyone? Okay, one. Uh, Hands up, people who use finite elements, but in the context of commercial packages like Abacus or COMSOL. Okay, rest of the crowd. Those using commercial packages, do you normally work with coding users or routines, or is mostly just using what is inbuilt in the? Maybe hands up those coding. Okay, a bit of so a bit of everything, I see. Okay, anyone doing something that has not been covered here, like maybe using open source packages that like Phoenix, stuff like that? Okay, okay. So yeah, I think we have a bit of everything. I'll see how I go through. Yeah, I think okay, let's get started and we'll see as we go along. So I think I have some slides on the implementation that maybe I'll skip some, I think. Well, the way I thought of running the course is we could do a small break of 5 minutes, I guess, at some point. I thought of dividing in two parts. One would be a bit of introduction to phase field modeling and phase field fracture modeling, and then a second part where we talk about applications. So maybe the beginning is a bit more dense, but you are more fresh. You just woke up or relatively recently, and then the second part that we are a bit more grilled. The applications are easier to follow. Just examples of what you can do with these techniques. Basically, that's the takeaway. And yeah, I think I've seen a good number of you at my seminar. But yeah, my name is Emilio Martinez Pañeda. I'm an academic at Oxford, and I've been working with this phase field fracture modeling for quite a while now. And I think in general, I could describe myself as a computational fracture mechanics person. I tried every method that was out there, cohesive elements, XFEM, remeshing. I think everything, almost everything I tried. There's many continuum dimension mechanics and so on. And every time it will be the same. I'll go to a conference, I'll see someone presenting some beautiful videos, some very nice images of cracks doing something fancy. And then I'll say, oh, that method looks very powerful. I'll go home, I'll implement it. And then, yeah, maybe I was able to reproduce those conditions. But then whenever I try to change anything, then things will crash. So things were not very robust because, well, modeling evolving fractures is a complicated business. So that's a problem that I faced. But with Facial, the experience was different. I think I first came across this at a conference in 2016. And I came back. It was first very easy to implement. So yeah, I could do that in the morning. And then I started trying things, and not only I was able to reproduce the nice things that I saw in the talk, but also all the things that I did, it came out quite easily and naturally. So, I mean, I have an open perspective, and I believe in the scientific method. Maybe 10 years from now, you'll be hearing me talking about something else. But at this point, this is by far the best thing I've ever seen when it comes to modeling interfaces and fractures as part of this. Yes, reliving is robust, is physically sound, it has everything. I struggle to imagine that something better will come along, but maybe it will. And well, I'll be very happy to embrace it. In the same way I was someone using cohesive elements all the time before this came along. But yeah, as I said, I was quite impressed, and I remain to continue to be quite impressed. So I'll tell you a little bit about this. Okay, so yeah, as I said, this is not just my feeling, it is really taking over. If you go to, I don't know, one of the latest the big computational mechanics conference is this World Congress in Computational Mechanics. I don't know if the last one was in Vancouver. I don't know if any of you were there, but they were like, I think it's 5 sessions on facial fracture. So more than on any other technique, computational mechanics technique. So it really has taken over the community completely. So you see here, I had to prepare this for a conference last year. So this is the number of papers in Google Scholar showing for phase field and fracture. And you can see that it's growing quite a lot. Since 2010, it was more or less when they developed, or Christian Mia developed some very powerful or robust ways of implementing this. And it's now exceeding 5,000 papers per year. So this is, I think this is now close to 90% of all computational fracture mechanics papers. Even though, things always there's always legacy work going on. So it's quite remarkable. It has really taken the community by storm. And I mentioned a little bit of this, but I'll expand a bit more in my seminar. So there's a few reasons for this. So phase field is not only useful for fracture, but it's in general useful for any interface. And modeling in computers, interfaces evolving is also quite nasty because, well, as you know, we like to have continuous things. We don't like discontinuities. We want, displacements. Our solution variables need to be continuous. And in the case of a fracture, then that means that there's a discontinuity and displacement. In any discontinuity that you have, if you have one phase, so in the case of fracture, this will be crack phase and crack phase, but it could be any other thing, right? It could be any other problem, material one, material two. Anytime you have discontinuity, if you treat the discontinuity as sharp of interface, this is a bit tricky because, well, in your computer, you need to know where that interface is evolving, where it's located. You need to know what happens if suddenly that interface coalesces with another interface. Sometimes you need to apply boundary conditions of those interfaces. So in my seminar, I talk about hydrogen, how the cracks grow and the hydrogen follows. So I need to know where the crack is because that will be what delimits the environment, where the environment is, where my hydrogen is and where the metal is. So any interface you need to be able to track it and you need to be able to put boundary conditions on it. And that's very nasty. So phase field methods open a way to go around this. And the idea is that instead of having this interface as sharp and discontinuous, then you smear that interface over a finite domain and use an auxiliary variable, the phase field, to describe where the interface lies. So basically say, okay, I'm going to have this variable phase field phi. It's going to be 0 in the phase blue phase, 1 in the red phase, and then it's going to change smoothly here in between. And this is natural because I think we know that also in physical reality, things do not change dramatically. There's always, how small your interface is depends on what physical problem you're interested in. Some physical problems, the interface can be very small. But in reality, we know things are not. So if we think of fracture, for example, we know that we don't only go from crack to uncracked material. There's some sort of area where you have micro cracks and so on. So there's always, it kind of represents what happens in reality, of course. And then the good thing about that is that then you need to basically tell your model how this phase field variable is going to evolve. And then that is kind of an implicit representation of interfaces. No longer you have an interface, you just have a variable that is evolving in your problem. And that has multiple advantages. One is that you define this interface, you're solving this interface equation in the entire domain. It might be that if you only have one phase, maybe the phase field is 0 everywhere, and that's fine, but you're still solving the equation in the entire domain. So you don't have any special treatment or here I have an interface, I need to do something, you just let it go, so to say. Then topological changes such as divisions or merging of interfaces are naturally captured. So imagine you have two cracks coalescing to each other. If you didn't have a method like that, you have to keep track of the crack and then eventually say, okay, crack 1 is approaching crack 2, and now something is going to happen there. And most of the methods that I used before, they struggle when it comes to those things because it's even industry that they use a lot of these remeshing techniques, they are unable to handle two cracks going to each other. Here, you don't need to do anything. You don't even need any ad hoc criteria. You define the physics when you define how this phase field equation evolves, and then naturally the cracks will interact with each other. We'll do whatever the physics tells you or whatever physics you embedded into that equation. And then the other good thing is that you can easily combine this with other equations describing other physical phenomena, so very well suited for multi-physics problems. You have an equation for the phase field, and let's say I was explaining the case of hydrogen, right? So you have a crack growing in a hydrogen-containing environment, let's say in a pipeline that stores hydrogen gas. The moment the crack grows, that hydrogen gas will immediately go there. You need to capture this in your model. Very easy because you know where your phase field is. You can solve for another equation, and you can make the variables in that equation depending on the phase field. So I can say the diffusivity of my material, or in batteries, for example, people say in crack areas we have no diffusion of lithium ions. Well, you just make your diffusivity depending on the phase field, since you're solving the phase field. In a way, you have a variable that tells you what things are happening, and then you can exploit that as you wish. And I'll focus mostly today on fracture, unless you guys tell me that you are interested in other sides of phase field. I have some slides on the corrosion side as well. Let's see if we have the time. Depends a little bit on your interest. But this technique was first originated in the condensed matter physics community. They use it for solidification, macrostructural evolution problems. And it's by far now the most widely used technique on this. So whenever you want to see any solidification problem, any macroscopic solution problem, phase field is the way to go. You see an example here where you have these two phases evolving. As I said, I'll focus mostly about fracture. These are all simulations, by the way. Yeah. And as I said on the seminar the other day, so there's a reason why it has become so popular in fracture. You can see here. So this is a very funny crack because it happens due to hydraulic fracture. You are injecting a fluid, and that creates these funny cracking features in some sort of rock formation. And then you can see that the phase field, this is at a time 0, and then a time later on, the phase field is able to capture very complicated cracking phenomena. You see here cracks branching, cracks coalescing with each other, nucleation of secondary cracks in multiple places. And then the other area that we've been quite at the forefront is corrosion. So corrosion is a very complicated problem to model because you have electrochemistry, mechanics, material science. But recently we have shown together with other groups in the US and in Asia that you can use this idea to simulate the evolution of the corrosion front. So here the interface is material A and material B. Here the interface, the phase field is describing is uncracked material, cracked material. Here what you have is the phase field is describing how the corrosion front evolves. So metal versus seawater, any aqueous electrolyte, any corrosive electrolyte or medium that you care about. But yeah, so this is one of the aspects. This kind of implicit representation of interfaces allows you to capture very complicated features. So that's one of the beauties. Of course, we want to make sure that the colors that we predict are not only nice colors, that they are in agreement with physics, right, with reality. And that is the other good thing about phase field, is that it provides, I would say, a sound background for or a computational platform for Griffith's energy balance. I don't know how many of you have taken a fraction mechanics course. Raise hands. Okay, not everyone, but almost everyone. Well, in fraction mechanics, normally the first thing you learn is that the father of the field was this man Griffith, Alan Griffith. He was a British engineer, and he said, well, a crack will grow not when we reach a critical stress, but when the energy stored is sufficient so everything has to be in agreement with thermodynamics. A crack will grow whenever the energy stored is sufficient to overcome the energy required to create tuner surfaces. And he postulated this energy balance. We said this is the change in potential energy over the crack. So the energy stored is this, and this is the energy that you need to create two new surfaces. And he did some experiments on glass where he showed this. And this he called the critical energy release rate, or some people call it the toughness as well, depends on what book you look at it. And this was great. Then we move a little bit away from this framework because it was a bit difficult to implement practically. So we move into stress intensity factors, which is what most engineers are familiar with in fraction mechanics, because it's a bit easier. You can calculate displacements or stresses ahead of crack. You calculate your stress intensity factor, and you compare with your toughness. But it's the same idea. It's just a different way of expressing this. And it comes with its own challenges. But it's just simply a bit difficult to handle this. However, some French mathematicians showed some years ago that you can formulate this into a variational form. So you can take this functional, and then you can express it like this. And then if you're able to minimize this functional, then you will be able to predict how cracks evolve like Griffith predicted, right? So strain energy density, energy stored versus toughness, fracture energy. The problem here is that you don't know where your crack is. You have here the surface integral, and you have no idea where your crack is. So this is where the phase field comes to your rescue, because the phase field is like a little bit like a damage variable. It acts like a marker. It tells you where your interface is. So you say, okay, I'm going to use the phase field. When it's equal to 0 means I have no crack. When it's equal to 1 means I have a crack, and things are varying in between. And then this allows you to regularize this functional. So now you have something that looks like this, where your surface integral became a volume integral. And this is something that I can easily minimize using numerical methods. And then I have the phase field is like a damage variable. So again, 1 means fully cracked. So when you have something that is fully cracked, then you have no load carrying capacity. So it's the gradient your strain energy density. Remember, strain energy density is stress multiplied by strain. And then here, the other aspect to note from a computational perspective is that it's a little bit like a non-local continuum damage mechanic models, in the sense that you have a gradient of the phase field and therefore a length scale, which means that you have an additional parameter in addition to this GC, this fracture energy. But it also means that if your mesh is fine enough to resolve this length scale, then your results are going to be mesh objective. So a lot of the damage mechanics work uses local models where you get a different answer depending on how fine your mesh is, because it will always localize in one row of elements. So that's a problem, a big problem. As you can imagine, you cannot just tell industry, hey, run these calculations, and then the guy sitting next to it will run with a different mesh and we'll get a completely different result. Here is not the case. As long as your mesh is fine enough, your results will be mesh independent. So that's good. It allows you to simulate things as Griffith predicted. And I'll tell you in a minute that this is the case. But basically, if you look at the strong form equations of the model, you have this. So the one in the top, for those of you familiar with mechanics, it will be, you'll recognize as the balance of linear momentum. So, Newton's law in continuum mechanics, so to say, where you have the divergence of the stress. I'm not putting any body forces or anything. And then the phase field is the gradient your stress. So you have a loss of load carrying capacity. So it's the regular thing that you do in any finite element package when you solve for the formation. But now you do have an extra term here that is like a damage variable that basically tells you, well, if you have no material, if you have cracked fully your material, then you're not able to sustain any load. And then you have an equation for the evolution of the phase field, which again is based on this, is basically the strong form of taking deriving this functional and discretizing. Well, no, without discretizing, this is the strong form of that functional. And then you see that it's basically a competition. Okay, the parameters that I care about, that I'm solving for, is the phase field. Then the other things that I have here is the strain energy density. We know that depends on stress and strain. That provides the coupling with these guys. And then the only two parameters that I have, the material constants, are the length scale and the toughness, the fracture energy. And yeah, once you solve this problem, this coupled problem, then it's very easy to get very complicated cracking patterns. You see here, this is a calculation in Abacus, but I have it in COMSOL as well. This is the growth of a crack that is branching due to the application of the dynamic load. So it's a dynamic load that brings waves, and that waves interact with the crack, and then you get these funny cracking features. But it's always like this. So you solve a finite element equation. This is the one you solve normally. You just add this term. You solve an extra equation, and that gives you how this guy evolves. And you know that if you plot that guy, it will go from 0 to 1, and you know 1 is fully cracked, 0 is blue is intermaterial point. And I have some examples here of taken from the literature that I showed as well in the seminar. So just showing how powerful the method is. I think I added one more. This is from a close collaboration in Zhao, is in cracking of particles. But I mean, in general, what you see, it involves multiple materials, metals, ceramics. This is probably NMC, so another ceramic, or graphite in particles, carbon fiber reinforced polymers, functional grade materials. This is a thermal shock problem. And you can see is that not only you can predict very funny, complicated cracking features, but you're also able to do so showing a very good agreement with experiments. I mean, if you look at here, this experiment was done for multiple cooling rates or different, I would say, temperature boundary conditions. And you see that even the crack spacing and the crack length that you see is almost identical. They compare for these all conditions. And naturally, the model is able to capture those things. You don't have to tell anything about the size of the crack or anything along those lines. So it's quite powerful. So it's physically sound because it's based on the thermodynamics of fracture. So this is the main two takeaways. And I'll emphasize this a bit more later on. Okay, this video is not running for some reason. But anyway, this was just a video of some cracks evolving. What I wanted to, yeah, go ahead, sorry.
So when you have the phase field equal to some fractional value like 0.25, is there a physically meaningful interpretation in your material? Like, could you measure the difference there?
Yeah, that's a very good question. And sorry for the guys following online, but I have to make use of this. Any of this work, otherwise I'll try my best with paint. So it's similar to damage mechanics modeling. So normally we say, okay, 1 is fully cracked, 0 means nothing happened, basically, intact material. So then the interpretation normally with this is that if you look at one integration point, one point in your finite element model, what it means is that it's a small micro scale domain. So it's like looking into a microscope and seeing your material. And if you think of the cross section of a bar, then if you were to have something that is 0.5, for example, it would mean that when you look at your integration point in your microscope, you will have half of the cross section. I don't know if this is half, but more or less half of the cross section will be damaged and the other half will be undamaged. So it provides a degree of micro cracking. Whether it's easy to observe, I mean, it's a bit difficult. But in general, people don't care that much about that because it's kind of an intermediate stage. They say, okay, I can see when the crack grows as long as I'm able to see that I'm fine in that sense. But that will be the physical interpretation. Somehow you have half of when you look in the microscope in that integration point, half of it has been broken if it's 0.5, a bit less if it's, yeah. Yeah, so the key two takeaways that I'll be emphasizing is these two. So it's a computationally robust method. So, very complicated. Any phenomena, no matter how complicated it is, 3D cracks growing in 3D, which is, for example, an issue for X-FEM, branching, coalescence, all of those things, and without convergence issues, which is quite interesting. And then it's basically is also physically sound, so it's based on the thermodynamics of fracture. As you know, Griffith postulated that thermodynamics in the simplest case, which was a mortal material, very brittle material, glass. But then Orwan extended to elastoplastic solids, so you can extend this to elastoplastic materials as well. It's not limited to brittle materials. And the other thing that I realized, or the good thing, is that it's in agreement with fracture mechanics theory. I'll explain in a minute. I will show you that in a minute. But a lot of the engineering standards, for example, say, a crack will grow whenever the stress intensity factor reaches the fracture toughness. So engineers do a calculation, they estimate the stress intensity factor, and then they make a decision on their design. So phase field will predict you exactly the same. It will predict you that cracking will initiate at the same time, but it also allows you to handle more complicated things. And this, I think, has been a deal breaker in its impact, particularly when we go beyond academia, because academics, maybe we don't mind having a model which were difficult to interpret, that you need a lot of calibration and so on. But in industry, they really need something reliable that depends on things that they understand, so fracture toughness, fracture energy, and things that are in agreement with what their current understanding. So the fact that it gives you good agreement with well-established fracture mechanics theories is a plus. And I'll show you that in a minute. So that is the first point I'm going to cover. Mathematicians have shown that this is the case. They use something called gamma convergence, and then they show that indeed, if you minimize the functional, then eventually you recover that condition. But as engineers, we had to do the simulations to confirm. So one way that you can do it is that you can assume this kind of a small-scale yielding. So you take the displacement solution, the Williams displacement solution. So those of you seen fracture mechanics will remember this. So for a given applied stress intensity factor, what is the displacement as a function of r and theta, the coordinates. So you can apply that any k or j, these are the same thing. You can correlate one and two. You can apply a k, and then let the phase field fracture model tell you when the crack will grow. If the crack grows when g equals gc or k equals kc, you can also put a c here and c there, then this means that your crack will grow exactly when fracture mechanics tells you it will grow. And fracture mechanics tells you cracks will grow whenever k equals the fracture toughness or g equals gc. So let's see what phase field does. And we can do it with this example because it's an example where we prescribe not a displacement or a displacement that gives me a given k or j that I know, a g, sorry, that I know. So then I just need to see, okay, I apply I start increasing my displacement, my k, my g are growing, and then I see my model crack growing, so I write it down. Okay, what j did it grow? Is it the same? It should be the same if it really is based on fracture mechanics. And this is what we saw. So this is the g at which cracking occur versus the gc that we input into the model. So it should be equal to 1, this ratio, ideally. And this is the predictions that we have for different finite element sizes. So this is the length scale, and then we keep basically reducing it. And then you see if your mesh is very coarse, then you get something that is garbage. But eventually, as your mesh becomes fine enough, you see more or less 7 times smaller than your length scale. Then eventually you converge to a given value, and that given value is, for all practical purposes, equal to 1. So yes, it is the case. We also look into whether cracks grow at when g equals gc, and it's a bit difficult because you need to have an analytical expression for this g as a crack grows. But for some cases, we know this. This is for a double cantilever beam where you can use Timoshenko's theory to estimate the energy release rate, so as a function of compliance. And then when you do that, this is two different phase field models. You see them more or less together. This is crack size versus this applied displacement. And you see that again, the beam theory solution based on this g or this j equals g when a crack grows seems to be in good agreement. So the mathematicians have shown it theoretically, but we have confirmed computationally this is the case. So the method predicts that cracks evolve when this condition is met. So whenever an engineer says, oh, my design standard says this will fail at this load, the method will predict exactly that and allow the engineer.
So basically, your fracture is evolve regardless of the mesh side you choose. Like you don't evolve in the actual direction, regardless of the mesh side you choose, like each.
You say if the crack is going to grow along the
expected.
Yes. I think that you will get results even if your mesh is too coarse. It's just that quantitatively, when you look at what load things, you over predict the load at which cracking takes place. So I recommend always doing a mesh sensitivity study. Here we know that some people in the literature say, if my mesh is 2 times smaller than the length scale, then I'm fine. Okay, that's somewhere here. Well, I mean, depends on how, how much you care about accuracy. I would say normally in my group we go for 5, 6 times because this is good enough. Some people say 8 times. It depends a little bit of your. So yeah, so you will get a result. It's probably not a bad one, but ideally it would be good to be in the safe regime in a way. And you don't have to do many trials because the length scale. I just need to make sure that your mesh along the crack propagation region, that's where you don't care, of course. You need to resolve that interface. Okay, then the other thing is that we have this length scale. Okay, so far you can say, okay, very good, Emilio. The model depends on this GC value. The GC value has a clear physical meaning, is the toughness, so that's great. I don't have to calibrate anything and so on. But what about that length scale that you told us before, right? The model has a length scale there. And that length scale is actually quite convenient because Griffith, when he postulated this theory, he always assumed that you had a crack to start with. But in reality, materials, sometimes they don't have macroscopic cracks. There's always some sort of crack, but it might be at the atomic scale. And what we see in materials is that they failed, sometimes dominated by fracture mechanics. So this is toughness dominated failures, but sometimes due to strength. Maybe you get the plasticity all over the place, or if it's a ceramic, you reach the strength of the ceramic and so on. And this is what comes naturally through the phase field. So in fact, if you take the phase field equation and you consider that you have an homogeneous 1D problem, like a 1 bar, where you have no gradients, then you kill the gradient and then you see that, so this term becomes 0, you end up here, and then you solve here for the phase field, you group terms, you solve for the phase field, you consider, again, 1D, simple case of a 1D bar, everything homogeneous. The strain energy density becomes 1/2 of stress versus strain, which is the same as this, Hooke's law, You carry that over, and then what you see that the stress, of course, is equal to Young's modulus strain multiplied by this degradation function. So the strain looks something like this. And if you plot this, you can also just take a 1 element or 1D bar and pull and see what you see in the fundamental model. But you see that analytically shows something like this. And the critical stress is this point here. That will be something like this. So in a way, this choice of length scale governs the maximum stress you can get, the strength of your material. And that's important because we know the materials, don't only behave based on toughness. The strength and toughness are both equally important. And it makes sense because, there is always a length scale related to fracture. Is the fracture process zone, how the damage distributes. And some materials will be very small, in others will be very large, but you always need that length scale into your model. And then so it makes sense that you have a length scale that somehow is an indicative of the fracture process zone, the region over which you have damage near a crack in your material. And when you input that, basically you get this sort of critical stress in there. And that's very convenient because these are simulations that we ran in a paper some time ago where you take a plate and you have different crack sizes, and then you change the crack size and you see at what load the things will fail, and then you normalize by this sigma c. So this is the stress of failure divided by sigma c, and you get these points, these red dots here with the phase field model. And you can see that it's quite nice because it goes from the fracture mechanics solution, and this is, by the way, what engineers do all the time. This is what they call the transition flow size. This is in all the nuclear standards. What they will do is they will do inspections. If their crack size is smaller than this point, they will use stress reaches some critical stress. So it could be von Mises, plastic collapse, if you're dealing with metals. If it's bigger than that, they will say, oh, things will fail due to fracture mechanics. We're going to use this K equal Kc or G equal Gc. And you can see here the phase field naturally captures those things. I don't need to tell the phase field whether I'm in one regime or the other regime. The phase field just naturally, you change your crack size and tells you exactly what the crack size, the failure stress is supposed to be. And I think that's quite important because it means that other fracture mechanics methods only work when your crack is big enough, when you are in the fracture mechanics regime. But the phase field will work no matter what size of the crack you have. You can have a tiny crack, it will give you the right result. You have a big crack, it will give you the right result, and everything in between. So that will give you some confidence that that you can incorporate those strength and toughness driven failures. And this is what you see. Well, this is the transition flow concept some of you may have seen in your fracture mechanics course. And this is what you see in materials. Right? This is experimental data points for various ceramics. And you can see exactly that. This is what the phase field predict is what you see in the experiments. You have a toughness dominated region and then a strength dominated region. And because we have the relationship between the length scale and the strength, we have both coming in there. Okay, so let me show you how this works in a practical case. So I think that I like very much what people call this blind test or this round robin test, because often academics, you see in academic papers that people present a model, and then they show some agreement with experiments, and it looks all very well fitted and so on. But it's easier to do that when you have, infinite attempts and you just calibrate things until you make it work. What is far more difficult is that without knowing the answer, without knowing the experiments, only knowing the experimental conditions, be able to predict what happens. So this is what I see that really, and people have done some, so both Sandia, and in this case is also Sandia with Purdue, but in Sandia in particular, I've been very active in coming up with this damage mechanics or fracture mechanics challenges. They say, okay, we're going to do some tests. All of you from all over the world can contribute with your favorite model. You tell us your predictions, and then we compare against the experiments. And those are very powerful because, again, it's very easy to have a model that fits an experiment when you have all the time in the world to calibrate it. But when you don't know what the answer is, that's a different, if you can blindly predict, that's a completely different story. So this is what I wanted to show this example. So this is basically something that Purdue and Sandia organized 2 years ago, a couple of years ago now. They basically 3D printed some rocks. Later we learned it was something like Ixon, but we didn't know at the time they said, we're going to 3D print some rock. We're not going to tell you what type of rock it is. We 3D print some rock samples. We will provide you a little bit data of that material because it's a completely new material and you have no idea what material is. So you need a bit of data. But then we will do another set of tests and we will not tell you what came out of those tests. We will just tell you these are the boundary conditions, these were the dimensions of the samples, but we will not tell you what came out of this test. You need to give us your results, and once we get the finite element predictions from everyone, then we will release and we will compare how people did. And basically what they gave you was a uniaxial compression test and a Brazilian test, I think, to measure compressive strength and tensile strength. And then they did some funny 3-point bending tests where they changed a little bit, they tilted the crack, they moved the crack a little bit. So that's non-conventional 3-point bending test. And they said, and we're going to measure with the IC crack trajectories. Also, one sample they measure with XCT. And then they also said, and we're going to measure for displacement response, and let's see what you guys can predict. So yeah, we took some of the information that they gave us from that Brazilian test and the compressive stress. And then we simulated the cases that they told us they were going to run, the experiments they told us. So they told us, okay, in this one case where the crack is going to be a bit to the left, another one to the right, blah, blah, blah. Well, we did everything they told us. This is the outcome of our simulations. And then this is the load versus, so this is the crack trajectories, this is the load displacement. And again, here at this point, we have no idea how the experiments look like. The only thing we knew was this Brazilian test and this compressive strength. So we sent this to them, and then months later, everyone sent their data, and then they released, and there's a paper comparing all the data, and this is what came out of the experiments. They did 3 replicate tests for each of the experiments. I'm showing here first force displacement response. So I think the agreement is quite good. Maybe here we underpredicted a little bit, but it's within the experimental scatter, I think, in all of them. So we were quite happy with this outcome. And then they released as well the crack trajectories. And you can see them here. I can put them next to each other. I think the agreement is pretty good. So this is why, from a physics point of view, this model impresses me, because it's able to predict things blindly, based on. Because it's easier for us. It depends on, we didn't know the material. If we know the material, it's even easier, because then we can go to a database and know which is the toughness, the strength. But we could fit those parameters to the Brazilian test, to the other one. So even without knowing the material, it was quite easy to be predictive. And then they did this case where they did a XCT scan, and they were going to measure in 3D how the crack tilted and so on. So we did a simulation with quite a fine mesh everywhere. We wanted to be sure that we predicted the right thing. So this is a crack. Because the crack is a bit oriented, it does a bit of funny tilting. You can see how the crack grows. And again, we send it to them. We have no idea what the final outcome was, but then they send us this as the XCT scan. So I mean, it looks, I would say, relatively decent. So this is the XCT image. Then they were converted into MATLAB, and then they put it against our prediction, and I think it was quite decent. They also compare displacements and so on, and things seem to be agreeing quite well. So yeah, I mean, there's always a bit of risk when you participate in these things. You don't know if you're going to mess it up completely. I think the first time Sandia did one of those for metals, there were some models that were completely off, and I think it was a bit embarrassing for people submitting those predictions, because then when it's released to the public, then you see. But I was confident that the model will work okay, and as you see, it did, I think, better than okay, I would say. So yeah, that was great. One thing I haven't discussed is plasticity. So you may wonder, okay, Emilio, in the case of an elastic string energy density, so you said the competition, how the phase field evolves is the energy stored in the material and the toughness. So in the case of an elastic material, then, well, all the energy stored in the material, the elastic one. What happens when you have a plastic material? Well, this is an ongoing area of research. So the first things first, the Griffith balance, the thermodynamics holds for both elastic and elastoplastic materials, of course. So this toughness that Griffith was looking into glass, so very low values of a few kilojoules per, or less than a few joules per square meter. Here, of course, it can be that this value is much bigger if you're dealing with a metal. That's fine. You just change that number. But you need to make a decision as well, not only in the fractal resistance, which is fine because we have, lots of data about how materials, what this should be, but also the driving force, because the idea is that in thermodynamics, only the energy that is stored in the material is available to create a new crack. So what do you do in plasticity? And this is an ongoing area of research. What we like to do is to take 10% of the plastic work, because there were some classic experiments by Taylor and Queenie where they showed that 90% of the plastic work is dissipated as heat, while 10% is stored. So we take that approach for plasticity. The other thing to take into consideration is that if I take you back here, one thing that you can say is, okay, Emilio, phase field is able to capture these two extremes. So the situation where toughness dominates crack growth and the situation where the damage is given by the strength. So in the case that toughness dominates crack growth, what matters is G being equal to GC. So maybe you don't really care that much about the length scale, right? We said before, we need our mesh to be smaller than the length scale. But we didn't say anything about the length scale. The length scale is given by the strength. So one situation you can say, okay, Emilio, what if I happen to have a problem where I know my crack is very big, I'm deep into this regime? Then I don't really care the value of the length scale that I pick, because that only governs this guy, and it doesn't matter. Cracking is going to happen before due to fracture than due to the strength. So why I don't just pick a length scale that is big, and therefore my mesh will be able to be quite big? And that's possible. And in some of the problems that I've seen people doing, for example, very large scale phenomena like ice sheets, fracture in ice sheets, people would take a very big length scale because they say, well, I don't really care. Fracture is going to occur due to G equal being to GC. And the length scale doesn't tell me anything about GC, or it only changes this guy, and this guy I'm not going to reach. So I'm fine with that. That's a possibility. But when you're dealing with plasticity, it's not as straightforward, because the strength is going to govern how much plastic dissipation you have ahead of your crack. So there's an effect of the strength on the crack growth resistance. You see here, this is basically your applied K versus crack extension. Depending on your length scale, you get different strengths as a function of the yield stress, and then you get much more plastic dissipation. This is the same as you can predict with cohesive element. This is a classic GMPA's paper by Tebergar and Hutchinson. So that's another way that you could calibrate your length scale in an elastoplastic material. If you have data, crack growth resistant data, you could just calibrate GC so that cracking starts at the right point. Cracking always starts when K equals K0, G equals GC. But then the dissipation will depend on your length scale, on your strength, on the size of your fracture process zone. So then you can calibrate the length scale so that you can predict whatever the experiment is. Okay, so that takes me to the numerical solution of these things. Why is the method so computationally powerful? So in general, the problem with fracture mechanics is that, as you know, the way we solve nonlinear problems, on the right side here, the way we solve nonlinear problems is that in finite elements, we always solve a linear problem, right? So we approximate a nonlinear problem into a nonlinear problem. So imagine that you have something that is, force versus displacement, and it looks something like this, something like this. So if you wanted to approximate this with one load increment in your finite element model, because you do something linear, you will basically be doing this. And then you will compute residuals, and then they will say, okay, no, there's an error. We are not able to. Basically, you will impose this displacement, and they will take it all the way here. And they will say, oh, the error is too big. This doesn't converge. So what we do is we break our nonlinear problem into many linear problems. So we do 1, 2, 3, 4, and then we take them in small increments so that, I'm doing linear problems, but I'm able to follow the curve. This is what we do basically in finite element. Right? We solve nonlinear problems into small linear problems. But the problem is that when you have fracture, what you often have is something that looks like this, and then boom, a big drop. Suddenly your material cracked, and you lost all the low current capacity. So for a Newton-Raphson solver, going from here to here is a very big jump. So normally Newton-Raphson likes things that are nearby. So it's a bit difficult, hence why all the methods struggle with convergence. This one works a bit better because you are uncoupling a little bit the damage from, they still couple, of course, the damage affects the stress and the The displacement will give you strains that are going to here, but you're somehow uncoupling the stresses and the damage, or the deformation problem and the damage problem. So in a way, it allows you to go little by little. So you say the displacement takes me here, I still don't get the solution, but then my damage takes me there, and then I get the solution, I go back to my displacement, it takes me here, and so on, and eventually you get to this point. So it can take a lot of iterations, but eventually you gain some flexibility by solving for your damage variable. And as you can imagine, there's two ways that you can solve this. One is what we call a monolithic approach. So you solve both equations at the same time. This is good because it's what we call unconditionally stable. So you can use big increments, and as long as you get convergence, you can trust that the result is good. But the functional, the phase field functional is non-convex with respect to both displacement and phase field. So this means that convergence is often quite tricky. So what most of the community do is to use what they call a staggered approach, where they solve first one problem. So you fix the phase field. So for a time X, my phase field is this. I'm going to solve the deformation problem. And now I fix the deformation problem and I solve my phase field problem. And then sometimes you iterate on them. This is what the people call it multi-pass or single pass. And this is good because for a fixed displacement, the function is convex with respect to the phase field, and the other way around. For a fixed phase field, the function is convex with respect to displacement. So convergence is very robust. This is what I was saying. These extra iterations that you get, this extra flexibility. However, if you use a single pass scheme, you may need to use very small time increments. So we suggested a new approach, which was to use monolithic approach with quasi-Newton, like a BFGS type of approach. And that one gives you the best of both worlds. You can get unconditionally stable, but you also get robustness. And just to show you some examples, so this is a classic example where you have basically a plate with a crack, and then you just pull, and then you see your crack growing. And this is a linear elastic material, mode 1 fracture, so your crack will grow all the way through. So if I plot here in red force versus displacement, you see that, right? The material is linear elastic, everything is linear, but then at some point, boom, my crack grows, big jump, and it goes there. And you can see that in blue, you see the bars is the size of the bar is the size of the increment. And then the height of the bar or the width of the bar is the size of the increment. The height of the bar is the number of iterations. So you can see that you can run the entire thing even though it's an unstable crack growth event in a few minutes in my laptop with 30 load increments. In fact, you can do it with 10. I did 30 just to show more precisely this part. But you can also see that with this method that we use, the critical time step requires more than 200 iterations. So that's quite interesting. Normally, you don't expect Newton Raphson to converge if you go beyond 5, 10 increments. But here, because of this flexibility, if you give it enough time, it will get you to the right solution. But anyway, it's quite fast. And then when you compare with the single pass staggered schemes, which can be increment sensitive, then you can see that indeed this appears to be much faster. But this is quite a specific of phase field, so I'm going to skip it for the time being. Let me speak in general. Okay, let's say that you like the method and you wanted to work with the method. How quickly would you be able to get this up and running? Well, for those of you that work with your own finite element packages, it's relatively straightforward. You do have an extra degree of freedom. So in addition to solving for displacement degree of freedoms, you have a phase field. The system is like this. The equations for the residuals of the weak form of your implementation, the discretized weak form will be something like this. You have the residual for displacement. This is the same that you have the same. So this is the strain displacement matrix multiplying your stresses. And then this is for those of you who have your own code and want to implement your own code, let's clarify. The only thing you need to add is this term here. So that's, it's not even one line of code. It's just adding a few characters to your code. Then you have the stiffness matrix for displacement is the same as usual. So again, strain displacement, stiffness, strain displacement. Again, you just add this extra term. So just editing one line of your code. Then you need to solve for the displacement, for the phase field. So this is how the weak form looks like. And then this is the residual for the phase field. So it's a scalar quantity. Yeah, you have a shape function, string energy density. It's not too complicated. And then the stiffness matrix with, again, B matrix and so on. So it's not that complicated for those of you not familiar with phase field. What if you are at the other extreme? If you maybe you're an experimentalist who wants to play with this but doesn't want to spend too much time learning how to code and so on. Well, phase field is built in console since version 6.0, so a few years ago already. I think now the version is 6.4, the latest one, but you can see in the 6.3, they have it here, phase field damage, and they have quite a lot of flexibility. So this is the the damage function. This is the history field, but you can pick. So they have a general form of the PD, and then I'm typically showing the conventional or standard face field model, but there are others. You could go and change this if you wanted to. So basically, you click some buttons. You see, you click here and say add face field, and then they let you pick a few options. So elastic strain density or total if you have a plastic material. GC, you define it. So it's a few options. It's very straightforward, basically. You click a few buttons, it's there. There's nothing. You provide GC, you provide EL, you select this, and then it will work out. Very straightforward. We published a paper also describing how to do it in case you're interested in. In previous versions, it was part of the solid mechanics inbuilt node. It still is available there. So you click on damage and you select damage model, face field damage. And then again, you say GC, this is the value of the length scale, this is the value of GC. So very straightforward, 2 clicks. And they have many tutorials and examples there. So it's very, very straightforward. I think that the main challenge that I find when using COMSOL relative to other things is that COMSOL has a lot of options when it comes to the solver. And any fracture problem, even though this is the most robust method I've seen on fracture, just because fracture brings that big drop in load carrying capacity, it will always challenge you, or they will always find one case where you say, wow, convergence is a bit nasty here. In other situations, I know better what to do in COMSOL. They have so many options, it takes a bit of time to. But my students and postdocs who work on a daily basis with COMSOL have found out a protocol that they will always get it to converge. So it's just spending a bit more time. And COMSOL, as you may know, is built on this idea, is built by mathematicians, and is built on this idea that you just define your PDE and automatically they'll do the derivation and discretization, a kind of symbolic differentiation. So you could take an old version of the phase field and then just define your own equation and then just define the terms of the equation based on that equation before. So it's pretty straightforward. So even if you don't buy that module in COMSOL, you can do it by yourself. I think this is being recorded, but I think I can say that I think the entire COMSOL could be probably reproduced just with the mathematics PDE model, because based on the idea that you have something inbuilt that you give them a PDE with your coefficients, and then they will take care of all the discretization and so on. If you wanted to do in Abacus, it's not inbuilt yet, although I understand they are in the process of doing that. It's a bit more difficult because the way the old school finite element packages are coded, if you want to add an extra degree of freedom like temperature or phase field, then it takes a bit more effort. But there's 2 ways basically of doing that in Abacus. One is a user element subroutine. So this is basically where you tell Abacus, give me the displacements. I'll give you the stresses and the residuals and the stiffness matrix. So basically Abacus with the user element will basically, the only thing it will do is assemble the matrix and solve. Or we found a way of doing it even easier through a UMAT subroutine. A UMAT subroutine is a user material. It's at the integration point level. And then Abacus basically says, oh, if you want to develop a material that you don't have in Abacus, I'll give you the strains, and you give me the stresses and the Jacobian, the material Jacobian, so the derivative of a stress with respect to strain. So I'll show you how it's very simple to do that. So remember, these are the equations, these are the coupling terms. So then the way we take advantage of this, or the way we implement this, and it's described in these papers, is we take advantage of the fact that Abacus can do couple thermomechanical problems, and the heat transfer equation, in a way, is not that different from this equation. So you can trick Abacus into thinking that temperature is your phase field. That's the idea. And then it becomes very, very easy. So this is the idea, right? So this is your equation. This is the phase field equation. I'm just rearranging terms. And if you look at the steady state heat transfer equation with a source term, is like this, right? So the variable you're solving for is the temperature. Here I'm solving for the phase field. Then you have this K. Okay, I make the K equal to 1. And then I have R. R is all of this. So it's basically expressing the phase field equation like this, and you can see immediately an analogy with so then you tell Abacus, okay, I'm going to solve a thermomechanical problem. And then what you know is that the temperature that Abacus is giving you is actually the phase field. And then you just substitute those terms. And if you want to see the code, it's less than 50 lines. So this is how, if anyone familiar with how UMAT works in Abacus? Otherwise I can skip it, or maybe I'll go quickly. But basically a UMAT is something like this. This is the entry of the UMAT, and then Abacus says, I'll give you the strains, give me the stresses. So you initialize, you say Young's modulus is property 1, Poisson ratio property 2, length scale property 3, GC property 4. Phase field is temperature, so temperature plus increment in temperature. You build your elastic stiffness matrix. So very straightforward, the usual. So this is what you will do normally if you want to do linear elasticity. Then you update the stresses and strains. So my new strains are, the old one plus the new one. New stress is the old one plus the new one. And then you compute the strain density. Strain density is stress multiplied by strain on 1/2. So stress, strain. You compute the degraded stress and the degraded Jacobian. So you just multiply by y minus v. And then the last two lines. So this is the same that you do normally with linear elasticity in Abacus. If you wanted to implement linear elasticity in Abacus, you will do that. You take Young's modulus, Poisson ratio. You calculate your stiffness matrix. You calculate the strains. From the strains, you multiply strains by your elastic stiffness matrix. You get the stresses, and then you update the stresses and the strains. This is what you will do. The difference here is that you do update also multiplying by the phase field. You degrade, of course, stresses with the phase field and the matrix, and then you have two extra lines only for the phase field, which is basically defining that heat source term, and also you need the derivative of the heat source term with respect to temperature. This is the equation. Remember, this is the equation you're solving for, and Abacus is thinking that you're solving this one. So you tell Abacus this guy is equal to 1, and this R is equal to this guy here. So you just define the R. So it's very, very straightforward. This is very, very simple code, as you can see. Just take advantage of this situation. One last thing I want to say. I think I'm going okay on time. One last thing. I'll discuss maybe very briefly the Phoenix one. You may wonder at this point, okay, Emilio, what if I wanted to, if I care about temperature, what if I had a problem where I have mechanical deformation, heat transfer, and fracture? Now I cannot use the temperature because you're using the temperature to trick it as the phase field. Well, there is another way, because you can tell Abacus to create two parts that look the same, and then in one part you will solve the temperature, and the other one you will solve the displacement and the phase field, with the temperature being the degree. And not only that, but a lot of extra physics problems, they can be expressed as a general heat transfer equation. So you can use that advantage to add more things. So for example, let's assume in general, you have mechanical deformation, the phase field, which I'm expressing in a very general way, and then any additional field. So if I look at the heat transfer equation, I can always try to find analogies. So for example, thermomechanical fracture, you need to model heat transfer. Okay, we can model heat transfer. Hydraulic fracture, where you have to model Darcy's flow, and this is the fluid equation. Again, you can always define each of these parts and find an analogy. Hydrogen embrittlement, you need a diffusion equation where you have, this is the change in hydrogen. This is some other extra terms. I showed you this in the seminar. You go to Abacus and say to Abacus, oh, I'm solving for temperature. In reality, it's hydrogen. You just define this guy to be equal to 1. You define this U to be C. And then you define this F to be this term here. So you can always trick Abacus, any general phase field corrosion, phase field fracture. And the idea is that it's all described in the paper. I don't want to spend too much time on something that is very specific to Abacus, because you may not care about Abacus. But what I wanted to say is that you can do these multi-physics problems in a very, very simple way with that little code, just by saying to Abacus, okay, I'm going to have two parts that are the same. And every time I talk about temperature, you think it's temperature, but I know inside that maybe it's temperature, but maybe it's phase field, maybe it's hydrogen diffusion, maybe it's fluid flow, whatever you care about. That's the idea. Okay, so I'll do 3 more minutes and then we do the break. So the last part is if you have your own finite element code, Phoenix, for example, how you do with a 100-line Python code. And again, this might not be relevant to many of us, but by the way, you can find all those codes, of course, online. But the way Phoenix works is that, well, you need to do some importing, some Dolphin Python package. You need to take the mesh out of somewhere. You define some discrete function space. Then you define some function space for displacement for the phase field. Then, I mean, it's very specific to Phoenix. I don't want to spend a lot of your time, but you see here, it's still a very small code. You take the mesh, you define those function spaces, trial functions this is the way, mathematicians will write a finite element code. You define GC, you define L, you define your two elastic properties. Then you say, okay, the first thing that you calculate is the gradient, the deformation, so the symmetric of the gradient of displacement. Then this is this. Then you calculate the stress as a function of the strain. This is Hooke's law. Then you define the strain unit density, in this case as the composition. You enforce irreversibility. I'm not going to introduce those topics. You apply your boundary condition. You apply the other boundary condition. I'm explaining line by line what you see here. I just wanted to give you an overview that is not as complicated as it looks like. It's actually relatively simple. And you change your concentration, sorry, your boundary condition, your displacement at the bottom is constrained. Yeah, you calculate, you define the solution space. You write the weak form of the displacement problem, so it's 1 minus phi. So you see the way you write in Phoenix very much resembles the mathematical expressions. Inner product of the gradient of V versus sigma U. So the gradient of V is going to be the deformation. This is going to be displacement. Then you write the weak form of the phase field problem, which is this. So GC by L by inner gradient of phase field by gradient of phase field. GC divided by L multiplied by 2. So it's exactly basically you're just typing things as they are. And then you define you solve the problem. And I think that's about it. You solve for the displacement, you solve for the phase field, you check convergence, you see how the convergence is, you check the L2 norm, make sure that your solution is similar to the other one, and then you plot everything you care about. So yeah, I'm not spending a lot of time on this because again, it's very specific. And the only thing I wanted to tell you is it is already built in many finite element packages. If you wanted to build your own code from scratch, just because you like coding, you could do it very easily. You just, if you have the finite element code that looks like this, normally you have defined this, coded this into your finite element code. You just need to add these extra lines. So it's very straightforward. If you like to work with your own finite element code, but in an open source package such as Phoenix, you can see that it's relatively straightforward. You just add a few extra lines to your standard finite element code. You can do it in 100 lines of code. So, for thinking of having a code that does absolutely everything, 100 lines is quite short. But life is even easier if you are using a commercial package. If you use console, you just click some buttons and it's there. You just define GC and L. And they have many examples, by the way. You can see the examples that they have online. And that will also give you a clue of what parameters converge better. In fact, on the newest version, they have a phase field explicit version where convergence is always attained. So even in quasi-static problems, sometimes quasi-static problems, you solve them with explicit. For example, in Abacus, if you were to solve Gorson model, they will recommend that you solve it with explicit because even if you're solving a quasi-static problem, convergence can be a bit tricky. So phase field, COMSOL has now phase field with explicit in the latest version of COMSOL. But again, you touch some buttons, you have it out there. If you want to have a bit more control, if you want to use Abacus, if you use this analogy with the heat source, then it's just adding 2 extra terms to your standard user material subroutine linear elasticity, which entire thing is less than 50 lines. So very, very straightforward, very, very straightforward to implement. Okay, then I think we can do a 5-minute break and I'll cover these applications, but in the 5-minute break, you tell me that there's something that you like more or you don't like, or you've seen in all my papers that touches another area that you care more about. Then I removed the hydrogen, by the way, because I imagine most of you have attended my seminar, but if anyone is interested in hydrogen, I could add it, or I could, not to bore the hell out of the people who went to the seminar, I could also give you a link of a YouTube seminar where I give it. We'll talk about hydrogen bits. Otherwise, I'll cover these ones over the next 15 minutes. And I do have a few others, and I put facial corrosion as well and a few other things. So let's see, depending on what you tell me, we could stop or continue. Okay, 5-minute break. Just now, we should follow, but again, if you have any particular interest, I'll be happy to bring some forward. One is batteries. I think most of you know how a battery works. So whenever you charge your battery, you have lithium ions. I'm going to speak, by the way, of conventional lithium ion batteries, not solid state. But whenever you have a charge your battery, so you have lithium ions that go from these particles in the cathode to the particles in the anode, and then electrons going the other way around. And then when you discharge your battery, lithium ions go here. And then when that happens, every time you charge and discharge your battery, then you have some reactions happening in those, then lithiation and deletion happening in those particles, and that triggers cracks, as you can see in this image here. And this is nowadays recognized as one of the main degradation mechanisms in batteries. So hence why we need to change our phones or our laptops every couple of years. So we try to model that with phase field. And we were not the first to do it. There was a group at UC Santa Barbara, Buck McMeekin, who had done it before. But they had only done for 1/2 cycle. And so they didn't account for the fact that, charging and discharging a battery is a cyclic process. So we incorporated the fatigue elements of it, or the cyclic loading. But basically, the idea is very similar to before. So you have these two equations that I showed you before, displacement and damage. Those of you who came to my hydrogen seminar will recall that we were modeling the transport of hydrogen as a change of concentration in time as a function of gradients of concentration and some gradients of hydrostatic stress. Is the same in batteries. The main difference between the hydrogen and the batteries is twofold. One is that hydrogen degraded very significantly the fracture toughness. This is not the case in batteries. You still get cracking just because you have something happening. You have mechanical loads, but it's not that much that the fracture energy is degraded. Some people did some atomistic calculations, so a little bit of degradation, but not that much. But then what you have is these chemical strains, which are also present in the case of hydrogen. But the difference is that this constant here, this partial molar volume, is one order of magnitude larger in batteries, in lithium-ion batteries, than it is in hydrogen. And therefore, this term here that in hydrogen we normally neglect is quite significant in batteries. In fact, it's not that the battery is being undergoing, sometimes they put a stack pressure and whatnot, but it's not typically that the battery is undergoing a lot of loading, like in the cases of the hydrogen components. It's just those chemical strains from the lithiation and the lithiation from those lithium ions coming in and out that are causing this nucleation of cracks. So this is where the driving force for the fracture occurs. But otherwise, as you can see, it's very simple. Similar problem as before. You add an additional transport equation. If you were to do it in COMSOL, you just click an extra bottom. If you were to do it in Abacus, you tell Abacus you're going to solve for the heat transfer problem and define these quantities, or if you want to do in your own code, just adding an extra condition. And then what we did was to add as well a degradation function, the fatigue. So remember, we're talking about so far about fracture, but you can also have situations where your material will fail before reaching the fracture load just because you do millions of cycles or many cycles at a lower load, or fatigue damage. I'll discuss that in a minute because that's an entire new field of phase field. But for the time being, I'll just say that we account for that as well. And then we simulated not only idealized particles, like spherical particles, but also we took some XCT images and meshed those XCT images and incorporated realistic particles. And then we did hundreds of cycles, and we do the cycle by cycle. So it's computationally heavy, but computers are big enough that we can do hundreds of cycles, which is relevant to a lot of these applications, like electric vehicle charging and so on. And then when we see what happens, so we see, for example, this is for 50 cycles, no damage. Oh, well, this is concentration. Here's the hydrostatic stresses. We see what happens. Basically, we see how, for example, this crack starting to grow after 60 cycles, keeps growing after 100. This is how it looks after 140. So then we can predict the evolution of cracks for any arbitrary loading condition, for any particle size, for any scenario that you're interested in. So then we use this to, in general, all these models serve two purposes. One is map safe regimes of operation, understand when bad things are going to happen, and therefore prevent engineers from operating in those regimes, but also to have platforms that we can use to test ideas quickly without having to do complicated, expensive experiments. So you can see here, for example, we can change the C rate and then determine under what conditions my cracks will not grow. We can also play with the particle radius, and we see that if my particles are small enough, then we won't have that cracking problem. There are other problems related to having small particles. But yeah, you can play with those things, basically. That's the idea. Of course.
So when you're cycling the battery, are you actually solving like an electrochemical transport equation, or are you just effectively cycling with strain?
It's a very good question. We've done both. So most often in the literature, I would say the mechanics people doing batteries, they will just take one of these particles and they will apply a flux, and they will say, I'm gonna switch on and off the flux or change the direction of flux depending on whether I'm charging or discharging my battery. And that will be that's how I'll come with the C rate and so on, and that will be the whole thing. So there's no Nernst-Planck equations, there's nothing along those lines. However, we work a little bit in corrosion, and we realize that in corrosion is kind of, it's an old discipline, so it's well established that you really need to account for the electrochemistry, because the environment that you get, so if you plot in corrosion, and they can do this kind of with local electrodes, they can do these measurements where you have maybe a metal, and then you may have like a pit or something like this, and then they can see that the electrochemical conditions here are very, very different than those that you get somewhere here. because you basically the ionic transport is precluded and so on. So any occluded electrochemistry will give you different conditions. So the battery community, which is applying a flux, like we don't care. It's the same here, here, here. We just apply the mechanics battery community. A lot of battery guys do electrochemistry, but then they don't do the cracking. So we actually have a paper under review now where we said, okay, is this a sensible approximation? Because people don't even discuss it, it's like they didn't think about it. So we simulated the whole thing with all the electrochemistry, battery Bormer and Planck and so on. And then we saw actually the differences were quite big. I mean, it depends on your seed rate and so on, but you both not only predict very differently the stresses that you get, but also your capacity, your battery capacity, if you put a number of cracks and so on. I think difference were on the order of 30%. So there's a big effect if you ignore the electrochemistry, which makes the models a bit more heavy, but I mean, it is what it is. So yeah, I think it's important to capture that interplay between but that's something that we just only recently came across. And because we were thinking of we knew in corrosion it matters, whether we must matter here as well. So yeah, this is a single particle, which is what most people have been done. However, we also thought, well, maybe we can go to the electrode level, not the full electrode, but we can go at the electrode level because we wanted to quantify not only the particles, but also other things that could happen. Right? You could not only have particles, but you have secondary phases, carbon binder, pores. You may want to play with the thickness of the electrode and see what his effect will be. And again, computers are getting big enough. We work with this is work together with my friend Adam Boyce and Paul Shearing, who's an academic who was at UCL now at Oxford, who's very good on the XCT imaging side of science. So they have very beautiful XCT images that then we can convert to finite elements, and then we solve. So again, solving those equations. This video is not working here for some reason, but it will just basically show cracks growing in 2D and 3D, and then you can obtain battery capacity. Now you see here, basically, this is the phase field. You see that the phase field is evolving, how cracks start to appear, and you see that you have a very heterogeneous electrochemomechanical response. So it matters where your particles are, and the thickness of the electrode and other factors. So, yeah, I mean, again, I don't want to spend too much time because maybe this is not relevant for everyone, but the idea is that you solve. You have a question or yeah? No, I guess the only thing I want to say is that the idea is that you can solve couple problems where you have fracture or any other phase change easily with these type of problems. And again, as computers are getting big, you can go to large scale phenomena.
I guess I was gonna ask you, do you consider, okay, now I see the current collectors as well and what potential?
Yeah, it depends on what paper you look at it, but in some of those we have the current collector, and some of the recent ones will be the full battery, but maybe we don't solve all the detail across the entire battery. We just have like a full battery, but then we only solve for fracture in certain locations or something along those lines.
But I guess also in like in terms of the boundary conditions, you're considering, like, even if you're just looking at a single kind of layer or area, you're considering kind of the stress conditions that would be there if it was like in a jelly roll, for example, right? Or
well, here the fracture was only predicted in the particles. So then, yeah, they are kind of stationary there, and most of the cracking comes to the chemical strengths anyway. So, I mean, you can simulate so this is taken directly from the XCT. So you basically segment. So you have some pore regions, you have some carbon binders. So the boundary conditions in that sense through the connection and come naturally through the XCT image, and then you have the chemical strengths on the particles. And then what we did was not only go up the scales, but also down the scale. So I think the people discuss whether maybe you could do single crystals as battery particles, and then you will solve all your problems, or will give you extra capacity or less cracking. Because we know that often cracking occurs through the grain boundaries. Or people are saying, what if we change the microstructure and maybe we make a graded microstructure, since we know cracking occurs maybe closer to the edges of the particles, or maybe we could change a little bit the grain distribution. So again, building on this connection with this group that do very nice XCT scans, we were able to integrate those particles, accounting for the macrostructure, and you can see how the phase field is starting to evolve along the grain boundaries. So you can not only predict, I guess the takeaway is that in these couple of problems, you can solve them not only at the macro scale, but also solving at the micro scale, solving those. So you can play around and then, again, determine regimes of operation, but also playing a little bit around and saying, what if I do a single crystal? What do I win? What if I change the microstructure? What if I change my grain size? That kind of questions. Okay, the other area is fatigue. and this is a very growing area in computational mechanics. So, and I think it has attracted a lot of interest because, as you will see later, we do cycle-by-cycle calculations, but fatigue damage, I mean, in some of these battery applications, we're talking about hundreds of cycles, but in others, we're talking about millions of cycles. And the idea is the same. So this is the function that I showed you before for the phase field, but now you have a degradation function that degrades the toughness. And that degradation function has a couple of ingredients. One is a variable, you need a variable that accumulates with your learning history. So that could be this alpha, that is your strength and density. And then you need to define how this variable that accumulates with time degrades your toughness. So you need to make a decision on this function, the shape of this function, and then the people who proposed this, which was Lauro de Lorenz's group at ETH, the first model they proposed a few years ago, they said, well, the simplest model we can do is one where you only need to define one material property. And that material property, we still don't fully understand what it is exactly. It's not as simple as GC, but it is something that tells us how easy it is for a given loading condition to trigger fatigue damage. So if I load cyclically a material, how quickly will degrade, basically. But what they showed is that by doing that and doing these cycle-by-cycle calculations, they were able to predict the main features of fatigue. So in fatigue, as you know, we have two types of experiments. One is what we call S-N curve. So you take a bar, you load it, and then you see when things fail, and then it looks something like this. So that came naturally out of the model. And then also they do fatigue crack growth, where this is the crack speed versus delta K. So they start loading, and then you get a Paris law regime, and then eventually you get the complete failure. So again, everything came naturally out of the model. So this was cycle-by-cycle modeling, but you do things as an experiment. You see things evolving as an experiment. All the other models that existed before for fatigue, they will be based on fitting data with a curve and then saying, okay, now it's going to grow based on this Paris law curve or whatever. So this naturally predicts those things. It doesn't need any fitting. We work in this field, and this was with a student, Aliasa Guamar, who was an industrial PhD student funded by Vattenfall, who are very interested in this because they want to extend the lifetime of offshore wind turbines. And the oldest offshore wind turbines in the world are now in Denmark, and they were designed to last for 25 years. So they are about to reach the end of their lifetime, and they need to make a decision on whether they will extend it or not. It's a very complicated problem to deal with. So they are thinking of using these techniques. And then he realized that this model was not as simple to get quantitative analysis. So you needed to add an extra parameter. But once you add an extra parameter, well, then you get this kind of S-N curves and Paris law. You can show that you can go from Paris law to S-N curves, and you can predict the experiment. And the beauty of this is that because irrational is similar to what I said before about the strength and the toughness. You can go from toughness to strength. So with phase field, you don't need to know whether you are in one regime or the other. You just put any size of crack and you know you'll get the right result. The same goes here in fatigue. So you can, we still have these two parameters that we need to fit because we don't fully understand them as well as toughness and strength. The field is still not that mature. But I can fit those experiments to a Paris law type of experiment, fatigue crack growth, and then I can predict S-N curves, or the other way around, because it's able to go from one to the other. And then, you can predict for different materials, different load ratios. This is comparison with experiments. You can capture the crack size effect. All the key features of fatigue come naturally from this thing. And I think the reason why a lot of people have been working into this is that it's also a nice playground for computational mechanics people, because computational mechanics people love to play with problems that are of interest. And then here you do simulations cycle by cycle. And I mean, you can see here, we're getting into millions of cycles. So even though computations are heavy because you need to have a fine mesh to resolve your crack, your interface, and you do cycle by cycle, still you are able to do things relevant to engineering practice. However, this is costly. It takes a lot of time. So there's a lot of people trying to come up with ways of accelerating this. In our group, we have three approaches. One is those quasi-Newton BFDS methods that I showed you before, and you can show that you can significantly accelerate calculations. The other one is what we call constant load accumulation. We take into consideration that maybe not all the cycles, only the tensile part of the cycle contributes to damage. And then we can combine this with what we call a cycle jump. So if you have something, an engineering component loaded for millions of cycles, it could be the cycle number 21 is very similar to numbers 22, 23, and 24. So maybe you do 20, 25, and you assume that 21, 22, 23, 24 are the same. Then 26, 27, 28 are the same as 25, and so on and so on. So you jump cycles. And then we have also some ideas on modified Newton and other approaches. But again, this is an entire community. There's a lot of people in computational mechanics trying to come up with clever ideas on how you can accelerate these calculations. But what I wanted to say is that nowadays we are getting to a point where we can do things quite nicely. So this is a problem where you see a crack that has a funny orientation so that it triggers a bit of a mixed mode crack growth under uniaxial tension. And this problem has a fine mesh, as you can see here. And we are talking about 3 million degrees of freedom in 3D. And we are able to simulate with a direct solver. So if you move into iterative solvers, you can get bigger gains, only jumping every 4 cycles, 600,000 cycles. So I think you're just getting there. I mean, we can do now 3D. This is a bit old. This is a Julia code that we have. They become quite popular. In case any of you is interested in Julia, it's all on the website. You can download it. That we are doing now with similar problems, a few million cycles. So I think it's reaching to a point where computers are big enough that you can solve fatigue sort of from first principles, not having to make any assumptions on how the crack will grow, how my loading will be. I just load as it has to be. And you can imagine how powerful this is, right? When we charge electric cars, we don't normally charge them all at the same time from 20% to 80%, and then we leave the charging station. Some people will come and put 10%, some people will put 80%, some people will just load a bit and then go. So every person has a different way of loading their cars, and it will change depending on the day, on how much time they have. So we need to be able to incorporate those arbitrary realistic loading cycles, which we know, into those models. So that gives you the possibility of resolving those problems. Okay, the other area that we work is fiber reinforced composites. I only have one slide on this one. But I think the beauty of this one is that we can simulate the microstructure. And this is important for a variety of reasons. But let me show you here. So what you see here in both experiments and the model is that we have a phase field variable for the matrix, phase field variable for the fibers, and then we have either a cohesive submodel, a phase field variable for simulating the fiber matrix, the cohesion, the debonding between the fiber and the matrix. And you can see that the model seems to agree quite well with experiments. But what is interesting is that, fiber reinforced composites, when you plot the R curves, the fracture toughness curves, even though the matrix is quite brittle, you get a toughening effect due to the fibers. So if you just test the matrix, and this is KC versus crack extension, if you test the matrix, cracking happens here, it's like a brittle material, no toughening. But when you test a carbon fiber reinforced polymer, you get something like this. And this that you gain, this extra toughening that you gain, is because the fibers are closing the crack, right? You have a crack here, but then the fibers are kind of making life difficult for the crack to grow. So you have this fiber toughening that people talk about. And this fiber toughening, we have never been able to model this because it's inherently a 3D effect. So what people do, and it's complicated, you need to model cracking and all these things. What people do is normally they do experiments, then they feed that experiment, and then they put it into the model, which is not very, very predictive. But with this, we were able to simulate, as you can see here, the fracture process in 3D. So naturally, it's accounting for the fact that the fibers are closing the crack. And therefore, you can, when you do the simulation, you get that curve without any fitting, without any experiment. And then you can take the model and say, okay, now what if I change the number of fibers that I have? What if I change the properties of the fibers? What if I come up with some bio-inspired architectures where instead of having fibers, I have other defects in between and so on? So all of those things you can do in the model. So I thought that was quite interesting. We also developed the first phase field formulation for shape memory alloys. I don't know if you're all familiar with shape memory alloys, but these are materials that remember their shape. They can recover the shape under the application of a load or a temperature. You see a couple of funny examples here. So you take a clip, you deform it, but then when you apply a temperature, it goes back to its original form. And this, they're quite cool materials. This occurs either due to temperature stress, phase transformations, basically. And people have been used phase field we propose to use phase field to model fracture, but people have also modeled the phase transformation itself with phase field. So the reason why you see these things is because you have a transformation from austenite to martensite. So whenever you deform, you go into one of the phases, but then you apply a temperature and you go back. So there's two phenomena that are relevant to this. One is what is called the superelasticity. The other one is called the shape memory effect. But the principle is the same. So whenever you apply a stress or a temperature, you move between one of the two, right? So here you see I start in 1. So I start in the austenite phase. I apply the stress. So suddenly when I'm in 5, I start seeing a bit of a change already. Sorry, I'm still in the austenite phase. Here I'm starting to change I reach this temperature here, this level, and then I start to change from austenite to martensite. And then eventually I get this martensite behavior. And then I can go down and I unload, even though I deform irreversibly my material, this is no longer elastic. I do reversibly change because I go back, get again back to the austenite phase and go back. Or if you are here, you can also go to the martensite, but then you reverse by applying a temperature. So you can take it here and then you apply a temperature and you go from here to here. So both options you apply, you basically move between this martensite and austenite, and you can move across those either by changing temperature or by changing stress. And this is what we call superelasticity and Sherman rayleigh. And this superelasticity is quite widely used for some materials like stents, biomedical stents, because you want to have something that can deploy large scale, but it will not bring irreversible deformations. You want big, large strains without irreversible deformations. But what matters in fracture is that because the phase fraction changes with stress, near a crack, your stress is going to be much larger. So you have this situation where you have one phase, then as you approach the crack is changing, and then you have the other phase. So that brings also some toughening effect. So this is what we did. We did this facial model for shim and alloys where we account for this phase transformation and the fracture. And then what you see is that naturally you capture that toughening effect. So this is the plate with a single crack that I showed you at the beginning, the one that had a big drop. Here no longer you have this big drop because you have this phase transformation and therefore you get a toughening effect. We also simulated a biomedical stent. This was the time that I was at Imperial in collaboration with Cambridge. This is a biomedical stent that fails due to fatigue. So we added the facial fracture and the fatigue to be able to see when failure will occur in that biomedical stent. Anytime you have your heart operating. And then also we look into some architecture materials, some metamaterials where they were 3D printed, so they have a lot of little defects. This is the red dots that you see here, and we're able to see how those defects evolve with the number of cycles. Other type of materials are functionally graded materials. These are materials that are interesting because basically you change properties in space. So you see here how the properties are changing in space, and this means when you have fracture problems that even if your crack is aligned along the mode 1 fracture process, your crack is going to find a mode mixity type of situation because the properties are changing. So it's not facing a toughness that is in one direction, it's facing a toughness that is in the other direction. And that hence why the crack is inclined depending on where you place your crack, and you can see that the experiments and the model seem to agree quite well, and you can do that in 2D and 3D. One that I find quite interesting is this ice fracture and sea level rise. So I think there's common, I'm actually giving a seminar on this in a couple of hours in the Earth Science department. So there's an acknowledgement that fracture mechanics is what drives sea level rise today. Basically, when you have what they call iceberg calving, when you have ice detaching from the ice sheet, then that removes this butt stressing effect and that elevates it. So it's the biggest contribution to sea level rise. But fracture mechanics in ice sheets is not very well understood because of the scales, right? If you look here, this is 10 kilometers. So these are very big ice sheets and very complicated fracture problems. So you can see these are satellite images. You can see these very nasty fracture problems. But these methods, I think, provide a way of coupling this. There's also a lot of interaction with water effects, hydraulic effects, and so on. So it's a complicated problem, but we do have a possibility of simulating this. And in fact, basically what people seem to be most interested in this field is two things. One is the growth of crevasses. So this is your ice sheet. Then you have an ice shelf. And then what you have is these crevasses. So these crevasses are these cracks, basically, cracks in the ice sheet. And there are basal crevasses at the bottom or surface crevasses at the top. And what people are, this is a surface crevice, by the way, you see it's gigantic. What people are afraid of is that since the temperature is going up because of climate change, then we're going to have more meltwater. And that meltwater is going to favor so the water has a tensile force, and it's going to favor the growth of that crevasse. And then when the crevasse goes all the way from the top to the bottom, then you get this iceberg calving event, which is what you want to prevent. And in fact, this is the first author of this paper was at Columbia back then, but she's now an academic here at Stanford. And what she did was to take fracture mechanics and say, okay, what if I have if my amount of meltwater changes due to climate change, and I'm going to have more meltwater due to higher temperatures, what places of Antarctica will actually be vulnerable to these hydrofractures? And it's a beautiful study. You can see a lot of areas became vulnerable due to this increase in in water. And what we did was to propose a phase field model for modeling this, which allows us to go beyond what one can do with linear elastic fracture mechanics. And basically what you solve is a pore mechanics problem. You solve the viscosity of ice, which is typically, it's kind of a creep law. They use something called Glen's flow law, but it's kind of a creep model. And then basically we solve a number of problems. The simplest one is one where you have a single crevasse. You have the ocean water. So the ocean is kind of compressing your ice sheet. So the crevasse doesn't want to grow. It's going from a tensile area to a compressive area. But if you increase the amount of meltwater here, that's why climate change will be bad. Then you have higher tensile loads there. So it might be that you overcome this compressive force and then you get the detachment of ice, the isobaric calving event. So we were able to simulate that. You can also do that with analytically. It's a simple problem with linear elastic fracture mechanics. And we were able to see that these phase field models agree with linear elastic fracture mechanics. Then we simulated what happens when you have multiple crevasses. Again, you can compare with some semi-analytical theory, and we're able to get good agreement. We then simulated what happens when you have basal and surface crevasses, how they interact with each other. Again, we can compare with some analytical estimations. I'm going a bit fast because I just want to give you a flavor for this. I don't want to get too deep into these things. We were able to then see what happens, how do they interact, how close they need to be to each other to interact. We also wanted to simulate how those crevasses are formed in the first place. We know that is some sort of creep damage. So we took the profile of a full glacier. This is a Helmholtz glacier. You see here kilometers and meters, so quite a big thing. You incorporated that, and then you simulated how this creep deformation evolves, and we had like a simple damage variable. We said, okay, the cracks will initiate when this critical creep strain reaches a critical value. And then, well, we learn a few things of where crevasses might initiate depending on the surface of your glacier. And then you can do this in 2D or 3D. Yeah.
For your like mesh here, what was like the length scale of the mesh?
Yeah, it's a good point.
Like really big.
Yeah, I haven't gone too much into the details, but there are some fail-safe models where you play a little bit. The equation is a bit different than the one you saw before. So there's some phase field models that play some tricks to make it a bit less sensitive to the length scale. Still, I mean, the length scale is a physical property because it tells you what is the fracture per zone ahead of the crack. But we play so the element length is half a meter, I think, if I remember well. So it's quite big. Normally, you would expect the fracture per zone of ice to be smaller than half a meter. That being said, is well, two things. One is, well, it is what you can do. The other one is that, as I showed you before, if you have already a big crack to start with, you're in this toughness dominated regime, and therefore the length scale matters less because there's no influence of the strength. So even though we know this is not giving us the right strength, that's not a problem because these are toughness dominated fractures. The ones where you have already big crevasses. If you're thinking of small crevasses, then I'm not 100% sure. And then we use these other phase field models, which are a bit less sensitive to the length scale. I think that's the idea. So yeah, we play a few tricks because otherwise it was unbearable, but it's a good point. And then you see here in 3D where you have crevasses growing. They first grow vertically, they arrest when you reach the compressive strength, and then how they grow horizontal. And there's some observations, I didn't include it here, but there's some observations that show this type of behavior. And then the last thing I want to say is that a big discussion in the glaciology community is whether, in fact, I can show it very briefly, very, very briefly. Let me see if I can, because I'm giving a seminar on this, so I can show just one slide. Yeah. So this is the ICCP report. So this is the sea level rise predictions as a function of time. And then you can see that they vary, of course, based on how many emissions you will have, low emissions, very low emissions, intermediate, very high. And then within a given level of emissions, there's some uncertainty, particularly when you go to long periods of time. And this is related to the fact that we don't understand these fracture processes very well, hence why we need these more robust models or bring some physics and fracture mechanics into this glaciology community. But you will see that there's something quite funny here. This red dashed line here, that will be catastrophic. That will bring us a gigantic elevation of sea level rise. And this is a low likelihood, high impact storyline, including ice sheet instability process under the very high emissions scenario. So people are afraid that under certain conditions, something very catastrophic will happen, and that will be horrible for everyone. And what this catastrophic thing is, what will happen here? We need to go back to. The catastrophic thing that can happen is this marine ice cliff instability. So their glaciologists are afraid, mostly based on historical data, not on mechanics, not on physics. They are afraid that millions of years ago, there was a situation where the ice cliffs were the height was so big that they started failing by their own weight. And this led to a runaway event because this thing fails, that exposes an even higher ice cliff. That fails, that exposes an even higher ice cliff, and then and apparently this happened in history at some point, or there's some sort of evidence that it happened in history at some point. And they believe that under certain conditions we are approaching this scenario. So they're afraid that, but of course situations are never the same, right? We cannot compare, even if you think of water temperatures and whatnot, you will never have exactly the same conditions today that you had a million years ago or whatever this happened. So we need a bit more physics, I think. But this is basically the idea. So this was published in a Nature paper some years ago, and there's a lot of debate in the community. I think the consensus now is that most people think that it won't happen, but there's a fear that it will happen. And if it happens, then you have this catastrophic event. But all this discussion is based on, or most of it is based on historical data. And like, so glaciologists are discussing whether the conditions now are similar or can become similar to those where these things occurred. But if we bring these techniques, then we will be able to understand when these things happen from mechanistic principles, right? From fracture mechanics, physics. So that is what we're working on. This is a bit more complicated because this is not anymore a mode 1 fracture growing. You have some sort of damage spread. So for that, we need to come up with a failure surface for ice. So we compare with some experiments, triaxial stress state that they did on ice. You can see here, very complicated cracking patterns being predicted by the phase field. But then you can see that the formation seems to agree more or less with ice. And then this is another ice condition where again, there's some sort of shear band kind of forming in a complicated cracking pattern. So we think that we have now a phase field model that is ice ready, that is being calibrated or has introduced this failure surface for ice. So now we're applying it to simulate this condition. And that basically allows us to determine, I'll discuss more in detail that in the seminar, but what heights we think will cause this catastrophic event. And so at this moment, we think that the heights are quite high. I don't think we will see that anytime soon. But anyway, that's. We also use this for corrosion-induced cracking in reinforced concrete. So again, a multi-physics problem where I think the beauty of this was, in the problem that we have with concrete structures is that things fail after decades of use. So there was an accident, for example, in a bridge that failed in Italy a few years ago due to corrosion. Yeah, that bridge has been there for 30 years. So things have happened after 30 years, but we cannot do experiments over 30 years. So what we do is we do accelerated corrosion experiments. And then we from those accelerated corrosion experiments, we try to predict what will happen over 30 years. And that's a bit tricky because the physics are different. So we want models that resolve the physics underlying corrosion and subsequent cracking. And when you do that, then you're able to predict experimental data, but then also understand what happens under natural corrosion conditions where you're not accelerating the corrosion, basically. That's the idea. We also look into carbon nanotube composites, or kind of smart materials. People want to use them as kind of new structural health monitoring techniques where you use them to predict this interplay between electrical fields and cracking. So you can simulate that. You can see how the electric potential, when you trigger a crack, you see this change in electric potential. So you could have this kind of composites there in a place, and if you have a crack, then they will alert you that something has happened. So again, you can incorporate this, and you can do this at the macroscopic level, or you can also do RBEs when you see cracking process there. And that takes me to the last 15 minutes. So that will allow me to touch. Okay, is there anything, if you have any other no requirements for anything particular for fracture that you want to see, I think I'm going to jump into this corrosion, because this corrosion problem is, I think it's interesting for two reasons. One is a different application of phase field. So now the phase field is no longer talking about fracture. It's describing, so you can see a bit more wide representation of phase field, not only its application to fracture. The other reason I think this is a very interesting problem is because corrosion is a very important problem for society, as you know. I mean, I don't know if you all cycle, but my bike has always corrosion problems. But it's a big problem for society, but it's also one that we've never been able to properly model with computers. I mean, it's still unsolved in many ways. We learn a lot through excellent corrosion science, through excellent experiments, but it's one that we haven't been able to solve with computers. So if I were a young computational mechanician, I will consider this problem as a nice one to work in, because I think, in a way, I mean, phase field application to phase transformation in the context of condensed matter physics, microstructural evolution, solidification is still a very, very active field. And I'm sure if you plot the paper, still growing quite heavily. But it's a field that started 20 years ago. So it's not a new field anymore. It's difficult to, it's useful if you don't care about the methods development. If you have a phase transformation problem where you want to understand the physics, then yeah, by all means, go and take the tool. But it's difficult to develop a new phase model for solidification because that hasn't been already done. In fracture, it's a bit younger field. You could argue this became popular maybe 10 years ago, 5 years ago. So again, the field is still growing very much, and you can still do contributions because it still opens questions. For example, fatigue is one of them, coupled with certain other problems. There's new applications. So there you can still contribute. But you could also argue that the most cited papers have gone through in the sense that they were the original phase field fracture papers. Corrosion is different. Corrosion, the first paper that had mechanics, so there are some papers without mechanics, a few old before ours, but the first paper that had mechanics was 4 years ago from a group. So it's really, really beginning of the field. I mean, it's growing quite fast. So a lot of people are jumping on it, but there's still lots of things to do and plenty of problems to work on. So this is, I think as a scientist, it's very difficult to identify where are going to be I mean, you can see if you ask ChatGPT what problems to work on, ChatGPT will basically tell you the hot problems. So that's easy to do. You just look at what are the hot problems, and you don't want to work in a problem that is not of interest to anyone and it has no potential. Working on hot problems works well for most people because, well, you jump on the wave and you ride the wave. But ideally, what you want to do is to work on a problem that no one is interested in that is going to become a hot problem. That's the ideal case. And that's very difficult, of course, to predict. I guess when the guys started, working with graphene, they had no idea they were going to discover graphene and that kind of stuff. So it's difficult to see those things. But sometimes you can see signs, and corrosion, I think, is one of them. The reason why I think this is going to explode in soon, it's already growing massively, but the reason why because it's growing from zero, basically. That I think the reason why I think it's going to explode and become as popular as phase field fracture, we're now seeing thousands of papers, is because corrosion is very important, and because the models seem to have quite a lot of potential, and because it's a new problem, basically. So yeah, so let me tell you a little bit, maybe 10 minutes before we finished, an example of what you can do with phase field applied to other problems. And this is just an example. So we were just discussing, I worked sometime in solid state batteries. So in solid state batteries, you have some fracture problems, but you also have other problems that are related to interfaces, which are not related to fracture. One is dendrite growth. You have dendrites growing. So a lot of people are using phase field for that. We were interested in understanding how voids evolve in the anode, in the lithium metal anode, because that's a precursor for dendrite growth. And we were able, and we said, okay, what are voids growing? Interfaces. You have one phase, the void, and the other one, the lithium metal. So any interfacial problem, you can bring phase field into the picture, and it will allow you to simulate it. And that phase field model for voids has become very, very, very popular these days, and industry is using it as well, and so on. So let me tell you about corrosion as an example of, okay, you have this idea of the phase field, let's bring it in. And again, just to motivate it, corrosion is a gigantic problem for society. So globally has a cost of 2.5 trillion per year. Only in the UK, that is a small country, we spend 46 billion pounds on corrosion failures across many sectors. Is often referred to as the biggest threat to the sustainability of metals. It often results in catastrophic failures. So this is the bridge in Italy that I was discussing before of the corrosion of the concrete or steel in the concrete. But yeah, there are many examples. This one was one that I remember very well because it happened when I was a teenager or a kid, even before being a teenager, and everyone will have to help to clean the beach from the oil that came from this corrosion problem. And yeah, in any case, it's kind of a long-standing problem, right? These corrosion failures occur to happen everywhere in well-developed countries where we have very clear standards and so on. We really haven't cracked the problem, and we learn a lot about the problem based on very nice, I would say, almost a century of experimental science. But we still haven't cracked the problem, mostly because in order to predict corrosion failures, you need a model that tells you whether corrosion failures will happen or not. And we don't have any models for corrosion. And if you go to the corrosion conference, you will find that 95% of the talks are experimental, and there's 5% modeling talks, which are mostly DFT calculations trying to understand one particular thing. There's no models that are able to simulate the corrosion process, the failure. And this is because if you ask to most corrosion people, they will tell you it's a too complicated problem to simulate. There's too many things happening. And they're right to a certain extent. It's quite a messy problem. So I told you before about the offshore wind turbines. The reason why they only live for 25 years is because they suffer from corrosion fatigue. So the process is something that looks like this. So you have pitting, so you have the development of pits at the interface between the seawater and the metal. Those pits grow, driven by local chemistry and mechanics, and then eventually you get this pit to crack transition and the propagation of a fatigue crack. So this is the problem, basically. This is what limits and the problem is that this is a very strongly coupled problem. Because what do you see? First, what you see a nasty interface. So there's a nasty interface evolving, but also the shape of this interface not only is driven by local chemistry and mechanics, but it will also affect the local chemistry and mechanics. So the pH will change depending on the shape of your interface. If your interface becomes more sharp, it will also trigger higher stresses, or more likely to get a fracture. And at the same time, how that interface is changing will depend on your mechanics and on your local pH. So everything is very strongly coupled. You cannot just make assumptions. And if you wanted to simulate, I don't have it here, but if you wanted to simulate this problem without using phase field, it would be very complicated. You need some sort of Robin boundary conditions. It will be very messy. So the idea is, okay, why don't we use the phase field? Now my phase field doesn't describe cracks anymore. Phase field equal to 0 describes my aqueous electrolyte, seawater, for example. Phase field equal to 1 defines the metal. And then you have if you wanted to simulate the simplest corrosion problem, so forget about mechanics, you have two variables, one describing the evolution of the corrosion front, how metal atoms are detaching from the metal and being lost in the seawater. And then the other one is the concentration of metal ions, which will be 0 far away in the electrolyte, and it will be 1. This is a normalized concentration. It will be 1 in the metal. And then I won't get into the details for the sake of time, but these phase field models for corrosion, they're a bit more like the Canhillier type of models for phase field evolution. So very similar to the microstructural models for phase change that people use in the condensed matter physics community. And basically what you have is two equations, one for the short range interactions. So this is the material dissolution, how metallic atoms are being detached from the metal. And as you can see, it's a kind of Canhillier and Allen-Cahn. This is the Allen-Cahn type of equation. This will be the Canhillier without the gradient. But basically what drives most things is this mobility coefficient. And you can show that for activation control corrosion, since we know the velocity of the interface, you can estimate, you can find that this mobility coefficient that drives your predictions is proportional to the corrosion current density. So you have some sort of physical meaning on the main parameter driving the evolution of your corrosion rates. And then what you could also have is the long range interaction. So it could be that the diffusion of metal ions also matters. For example, in corrosion, they see a transition from activation control corrosion to diffusion control corrosion. This is when your kinetics of corrosion want to go through, but you don't have enough metal ions, so you saturated your metal ions, so you need to wait for the metal ions to diffuse far away into your electrolyte. And again, things depend here on a diffusion coefficient that you can measure from experiments. So let me show you how it works. This is the simplest model, what we call the pencil electrode test, where you have a piece of metal and a solution. And this is kind of the thing is protected, so it's kind of a 1D corrosion problem. And this is what you see. So the phase field is evolving like this. So you see how the corrosion front is evolving, how you go from electrolyte, how the metal is losing its metallic ions. So you're losing material. And here you see the concentration of metal ions from very small far away in the electrolyte, where you are diluting those metal ions to quite high here in the saturation concentration in the metal. And then the beauty of this problem is that because it's a 1D problem, for the case of activation control corrosion, it has an analytical solution. So you can see that the model predicts quite well the analytical solution. And then you can also see that the model can naturally capture the transition from this diffusion control corrosion to activation control corrosion. So my mobility coefficient depends on my corrosion current density. So as I increase my corrosion current density, there's a point where corrosion kinetics happen fast enough. And what is the rate limiting step is the diffusion of those metallic ions into the electrolyte. So you go from this linear behavior of activation control corrosion to this parabolic one of diffusion control corrosion. And of course, in this regime, things are dependent on the diffusion coefficient. So you naturally can go from one to the other. And I'll just finish by saying that those guys from the corrosion science community that say that corrosion is too difficult to model with computers, they are right to a certain extent. Corrosion is quite complicated, but these techniques really give you new horizons. They give you new horizons computationally. So you can simulate not only, the growth of, we're not interested in modeling 1D problems. You can simulate things in 2D and 3D. You can simulate the growth of pits, intergranular corrosion. You can simulate the growth of when you have the corrosion, when you have secondary phases, unsealable secondary phases that will not corrode. You can simulate pit interaction. All those things come naturally and for free into your phasing model. And the good thing is that you can also simulate the physics. So yes, corrosion is very complicated because there's a lot of physical things happening, all of which are important. You may have your electrochemistry is evolving as your corrosion defect evolves, but you can simulate. We know, the electrochemical equations, the equations that describe the electrochemistry of electrolytes are well established. We can add those and combine them to corrosion. Macrostructure matters, particularly anisotropy. You have anisotropy not only in the mechanical properties, but you also have anisotropy on the corrosion potential. You can incorporate that easily into your model. Mechanics plays a role through various ways. It accelerates corrosion kinetics. It also induces film rupture and repassivation mechanisms. You can incorporate that as well. You can have oxide formations, secondary products forming during the corrosion process. Again, you can simulate that. There's another interface, so another phase field. You can have hydrogen ingress into your sample, and that will also cause embrittlement. Again, you can simulate those reactions happening and how this triggers the evolution of cracks. So yes, corrosion is very complicated, but I think there's a good opportunity now to incorporate all this complexity. And it will come at an increased computational cost, but this is something that we can afford these days. So yeah, we incorporate a lot of these things. Things that we like to incorporate is the mechanical influence, for example, that we care quite a lot. So mechanics influence corrosion in two ways. One is in accelerating corrosion kinetics. You see this here, comparison with experiments. Not only this graph shows a good agreement, but also this micrograph here, looking at a defect with given dimension, same scale, you see that more or less the morphology is the same. The other way in the mechanics impacts corrosion is that in corrosion-resistant materials like stainless steel, for example, you will create a passive film that will prevent the material from corroding. But if your mechanical load is big enough, you'll rupture the passive film, and then you need to repassivate again. So it's a kind of a cyclic process. You can solve the mechanical problem. You can define a critical strain at which these things happen, and you can simulate that, and you can capture, the competition between loading rates and repassivation kinetics. The macrostructure that I mentioned before, not only the mechanical properties, but you can define a grain orientation dependence. So you have battle-warming kinetics here, and you can define a grain orientation dependent corrosion potential. Again, I'm going very fast. I don't expect you to catch all of this. It's just to give you a flavor that all of these things can be incorporated. Then you can have these kind of different microstructures. You can see how this pit that grow in a symmetric, nice way in this isotropic system. Here is a microstructure system, so it's an influence on the microstructure. Then we can do it to identify under what conditions do we actually care about microstructure, and what conditions we can use a cheap isotropic model. So we create these sort of maps. We look into 3D printing. 3D printing brings different microstructures that bring different behavior in corrosion, so we can understand what this happens. You can combine all of this with electrochemistry. So, Nernst-Planck equations for as many ionic species as you care about. That allows you to capture the effect of the solvent concentration, of the applied potential, of how these things change as your pit evolves. And I think I'm going to finish with this example because one that I like quite a lot. So there's an entire community dedicated to something called biocorrosion. So the idea is that if you break your leg now, they'll put you an implant, and normally they'll put titanium for that implant. But the problem with titanium is that it will remain there forever. So when you go into an airport, it will make a noise when you pass the scan. And in kids, it's particularly problematic because as the bone grows, they need to do another surgery to remove the implant. So what people in this community are hoping is that they can use a material that will degrade naturally into the body fluid, like magnesium. And then you put it there for as long as it needs to be, and then it hopefully will disappear and nothing will happen. So this is what you want, basically. This is the stiffness. You want your material of your implant to degrade as your bone or tissue reheals. And then at some point, whenever your bone is strong enough, then, this degrades into your body. The problem is that magnesium degrades too fast. So it doesn't really look like this. It looks something more like this. So there's not enough time for the bone to reheal or the tissue to reheal. So there's a big community trying to figure out ideas on how to do this. For example, you could think of alloying. You could think of having composites of magnesium and other biodegradable materials. But it's a slow process. And of course, we cannot do experiments on humans. Even on animals with this is complicated. So it's a slow process and a difficult one. But if you have a nice model, then that reproduces what we think is the physics of this process, then you can do you can validate in vitro the model and run then in vivo simulations. And this is what we do. So we have a phasing model for degradation of magnesium in body fluid, and we can change the electrochemistry. So we know that what we use in the lab is not exactly real body fluid, but we can change that electrochemistry in our model, and we can see that we can predict relatively good agreement with experiments, and then we can predict what happens in realistic, this is a stent and realistic geometries in body fluid. That's all. I understand that it's been a big rush, a 1 week course condensed into 2 hours, but hopefully give you a flavor. I mean, you don't need to grasp things. All of this is very well described in books, in papers. All our codes are openly released. We have codes in C++, MATLAB, Julia, Phoenix, COMSOL, Abacus. COMSOL is implementing almost everything that we do, so you have it all inbuilt. So yeah, there's plenty of time if you're interested in any of these things. But yeah, if you have any extra questions, happy to take them. If not, hopefully you got a glimpse of what is available out there, and then if you ever need it, then you know that you can always get where to find this information, basically. Okay, thank you very much.